Ciao! Here is a conversation with Emmanuel Blazquez. Dr. Blazquez is a postdoctoral research fellow in advanced mission analysis at the Advanced Concepts team of the European Space Agency in Noordwijk, Nederland. His research areas are advanced mission analysis studies with a focus on onboard real-time optimization assisted by artificial intelligence. He also works on autonomous guidance and control architectures, multibody astrodynamics, and system identification. We start talking about the structure and goals of the Advanced Concepts team, its interactions with ESA and the role space community. We talk, as it is often the case in this podcast, about the synergies between dynamical systems and artificial intelligence. In particular, we talk about the use of classification techniques to investigate chaos, focusing on Poincare maps, starting from the relevance of chaotic dynamics in trajectory design. We talk about potential interplays between convexification methods and artificial intelligence in the context of optimal control and more in general for rendezvous, and how this has implications for the use of the lunar gateway. We also talk about the use of GPUs in space research, talking about the asteroid aggregation problem, and the hardware he is using to conduct his work now. I hope you enjoy it. To support this project, please subscribe to my YouTube channel, connect with me on Twitter and LinkedIn, and support me on Patreon with a monthly membership, following the links in the description. So thank you very much for joining this conversation. As we have already started doing, I always start, let's say, chronologically, interviewing people, because I think it's interesting for listeners to understand how they arrived where they are. But for you, I think it's better to speak spatially. I don't know if that makes sense, but thinking about your surroundings in space, in some sense, now, and discussing the work you're doing at the advanced concept teams of ESA, and how your work relates to the work of other people there, how this relates to what you've been doing previously, and things like this.
Okay, sure. So as of right now, I'm a research fellow at the Advanced Concept team of ESA. So I just joined the team very recently in early September, and my focus is on mission analysis, autonomous GNC systems for space applications, mostly in orbit servicing, landing, these kind of things, and AI for space applications in general. So that's the focus of my research. And more specifically, I focus on onboard real-time optimization, using a mix of AI-based techniques and successive convexification-based techniques. Right. Also focus a lot on system identification and generally also guidance and navigation and control architectures for new autonomous space systems. Mm-hmm. That's the focus of my work as of right now, let's say.
Right. And are these all, I mean, you mentioned quite a lot of things. Are you approaching them in parallel, or is there some like unification idea?
Yes. I mean, I will probably talk about it a bit, but I try as much as possible in the projects that I choose to have as many of these disciplines come together. Right. And also I like to be involved in all different kinds of projects with different colleagues that can give different perspectives. So that explains also a bit why I'm within my domain. I'm a bit spread out within my domain.
Yes, and I guess that's the point of the advanced concept team.
It is, exactly. It is.
To have a multidisciplinary. Your background is aerospace, of course. Even going back to the master and the bachelor.
Yes. Yes. I did actually 2 masters, one in aerospace engineering in France, and one in space engineering in Politecnico di Milano in Italy. So it was at first aerospace focused, and then it became very, very space focused at the end of the studies. Yeah.
And so, can you say a bit about if there are interactions with other people in the advanced concept team? Or even with, I know you are a test tech, right? The physical place is the same, Noordwijk. So are there interactions with them or even with ESOC, other groups in ESA?
So the way the advanced concept team works is a bit different from the rest of the teams at ESA, I would say. We are really meant to be the think tank of ESA. So we have to come up with these disruptive new ideas that are supposed to have a long-term impact on the space industry. And the way we work is different in the sense that we are a bottoms-up team, right? Like we do not receive, we can receive some directions in which we need to orient our research from time to time. But most of the time we are free to choose the most promising directions that we think of for research. And we provide our ideas to the other teams of ESA. That's the way things work, which also explains why we're also multidisciplinary, because we have to cover a wide array, of research disciplines. And we also need some fresh ideas that come usually from people that are not from your own discipline. Sometimes when you need innovation and disruption, it's good to find it from some other place. So also explains why the team is the way it is. We have mostly research fellows, so postdocs like me, YGTs that stay there for 1 to 2 years, and only 3 permanent members in the team to keep the ideas fresh. So the idea is we work on this, kind of short-term projects that can take any time between 6 months and 2 years. And then we provide our feedback to the other sections of ESA where we think it's relevant. In my case, for instance, I interact a lot with the GNC team at ESA, Tech SAG. First, because some of them are my friends since I did my PhD mostly in that section, so that helps a bit. And also because in terms of the research that I conduct, they are the ones that are the most interested and that get most feedback from what we do, at least in the projects where I am involved. But then other people work with other sections, the debris removal section of ESA, for example, ESA Clean Space. It depends. It really depends on the projects. But the idea is we try to get as much output as possible to then give to them, and then it's their job, to give an impulse to the industry to go in that direction or that direction and make things happen and actually fly in space. So yes, we interact with other teams, but usually when we have enough to say and to tell them, when we're sure enough that a research venue is worth going further.
And you said it's bottom up. Is it even that you can apply and propose the topic of your postdoc, or was this proposed by the theme itself?
It's a good question. Well, obviously, when you apply, you come with a research plan, like any postdoc. But it's, I would say, the idea is you propose a research plan. You're not, you're allowed to not stick to it in the end, but it has to be coherent. But it can go any direction that you want, provided there are only 2 criterions, let's say, for a project to happen in the ACT and as a postdoc. The first criterion is it has to be interesting and worth researching. But that's true for any research project, really, right? If your idea is not very good, then the project stops there. The second criterion, it has to be completely new and disruptive. So if it's been done before, then it's not worth pursuing. Provided these 2 things are true, then you can do pretty much anything you want. So in my case, I had a research proposal based on finding synergies between AI-based guidance and control techniques, and successive convexification, which I explored during my PhD. And that's one of the things I'm working on right now. So yes, you're completely free to propose your research projects, and you're even strongly encouraged to propose research projects that have nothing to do with what was done before in the team. And also, embark on your journey, other people from the from the team from different disciplines to come and help you and provide you with a different kind of expertise.
Right, great. And to go into the details, let's go with my interest first. I'm interested in convexification, okay. So I would like to talk a bit about that. And let me say that I discovered that, and correct me if I'm wrong, I discovered these ideas in my master when we were discussing about the guidance and the application of convexification in the context of the SpaceX main stage landing.
Yeah,
is that the case? Yeah,
that's how everyone gets introduced to these kind of techniques usually. That's how I got introduced to them.
You're using convexification, correct?
As far as I understand, yes.
Yeah, okay. But your focus is guidance more in general, not only landers.
My focus is more, exactly. My focus is guidance in general. Yeah, because then in the end, the dynamics can change, but you're always facing the same kind of optimal control problems, right? You're gonna have some different kind of path constraints, terminal constraints, dynamics, but in the end, it works pretty much the same. So landing, it's because it was a practical need. Like autonomous landing was one of the first directions in space research for the new kind of autonomous systems. But now we are extending this new autonomy to other applications. Like in my case, I investigated the rendezvous and docking, but you can think many other applications. So landing was just, let's say, the start, really.
Yeah. So you mentioned about you mentioned the synergies between AI and these convexification methods. Do you have already a clear idea of how to exploit these and what these are when you started the research, or are you now exploring this? Was this a guess? Let's say an informed guess.
Well, yeah, it always starts with an informed guess, right? let's say my background is more because what you want to do when you want to study synergies between two kind of techniques, you have to understand them both very well before even trying to do this, right? So let's say my first steps in the AI world are quite recent, and I could see, I wouldn't say drawbacks, but some of the inherent flaws of these kind of techniques for at least for the specific applications I was interested in. So the first part of the research that I'm doing is mostly focused on, even before looking for synergies, just comparing them fair and square, like, having a landing scenario, for instance, where you can just use both these techniques. And the first question is, do they both work? Yes, okay, then we can move forward. Otherwise, the comparison stops there because there's no point. And then, okay, how did they compare in terms of resources that are used, in terms of how well are the constraints respected, in terms of how many constraints can you actually input? Can you actually use all kind of constraints with this technique or with the other? How well are they respected? All these things. So the comparison comes first, and then you can look for the synergies. But basically, the convexification techniques are very impressive as soon as you use them, especially for landing problems. They work also very well for rendezvous problems. But as you start adding constraints, then you can see that some flaws begin to appear. The flaws that are inherent not to these techniques, but to all trust region techniques and classic, techniques that rely on discretization. So the idea would be to relieve some of these flaws with AI, or at least to have a kind of hybrid GNC system that would give more authority either to the AI's based guidance and control, or to the other side on the pure convexification side of things. So those are the directions that I'm looking at right now. Again, it's still pretty early, but that's the informed guesses that I'm making and that I'm at least observing.
Yeah, and the goal is to have autonomy as much as possible because you want to reduce the computational cost and you want to be able to do things on board.
Yeah, the idea is basically this is a common trend, I would say, right now in the space industry and in guidance and control in general, is we tend towards autonomy, right? We started with landing, which is already pretty complex, but from a dynamics point of view, especially from a constraints point of view, it's not the most complex thing you can do. When you move already to rendezvous, which I have more experience in, you can already see that the problem is much more constrained, and well, it still works provided you give it some extra love and some extra work, of course, but already in terms of resources that you use, it's already not the same thing, right? And we need these systems to be autonomous in the sense that they need not to rely on ground commands or manual commands as much as possible. And also we want them to be, like I said, completely reliable and fault resilient. This is also a very strong axis of my research, is how do you ensure that these systems are have a fault tolerance, right? You can solve this in all different kinds of way. You can have, for example, autonomous guidance system backed up in a closed loop with a robust control system that will ensure that you'll tolerance to a certain kind of fault, let's say. Or you can do it just in open loop, like apparently some applications are done for landing with a complete open loop system. So these questions are still open, but the idea is to have increasingly complex operations done autonomously on board, because we will actually need it just for future space missions. So the sooner the better.
Yep, right. So changing topic, as you introduced before, there are different avenues, and one of these is the use of AI and in general classification techniques for the study of chaos via the Poincare mappings. Can you introduce this work and how you came up with this idea?
Yeah, so the idea is actually not mine. The idea came from one of my colleagues and boss, Dario Izzo, and one of our collaborators, Francesco Biscani, who used to work at the ACT as a research fellow some years ago. Now he works at the Max Planck Institute for Astronomy at Heidelberg. And they came up with this idea in a discussion that how cool would it be from, this very commonly seen in pretty Poincare maps, you could extract some interesting properties. I think that's really how the idea originated. But it turns out that when we discussed it afterwards, when I joined the team in September, the idea was a bit deeper than just one that comes up in a random conversation. We thought that really there were some interesting venues to explore because, well, as you all know, Poincare maps are subspace representations of systems. So what would be really interesting would be, can we use lower dimensional representations to actually extract properties of the general system itself? and to have an idea of how this subspace interacts with the global system itself, you know. So that's how really the idea emerged, and we refined a bit more the idea into two. Let's say we had two separate objectives. One of the first objective that we have is, can we classify? By classify is, we can start very simply. Can we easily find from a Poincare map if the system is chaotic, is not chaotic, and then classify also with respect to which degree it is chaotic, right? So really find some promising chaoticity in the indicators that are compatible with classical machine learning techniques, and then we can extract from these Poincare maps. The Apollinaire exponents, for instance, come up as the very first choice that everyone thinks of. But we hope to start it actually in February this year with some promising results coming soon, hopefully.
Nice. And so the idea is more about the study of, from a dynamical system perspective, it's really general, not applicable only to space.
No, yeah, exactly. So my interest in the project comes from obviously dynamical systems applied to space, since I'm very familiar from my research with the three-body problem.
Right.
In this context, of course, I'm interested in the general dynamical system side of things. Our idea is actually to start with a very simple 2D system that has nothing to do with orbital dynamics, right? The Artwood machine. So something quite simple. But then the idea is, provided we find some, again, promising research possibilities, to extract the kind of information that we had from these simpler cases and apply it to more complex 3D cases. For example, I would be extremely interested to see what are the applications to mission design, and specifically mission design to liberation point orbits. Can you, from the classic Poincare maps that you can find in any three-body problem book, extract properties of the system itself, extract properties of the orbits in the region around which the Poincare map has been a snapshot, kind of, these kind of things. So we start low level, and then progressively we build up to space applications.
Right. Right. So if one were to ask you what's the practical usage of this particular work, it's about trajectory design.
Yeah, let's say the first immediate angle that I can see is about trajectory design. But something maybe a bit less apparent that I see is also learning more how neural networks can help us in understanding chaotic systems, especially in lower dimensions. That I would say are the two main objectives of the project from a very practical point of view.
Right. And why specifically the use of Poincare maps? I mean, why studying systems in a lower dimensional space? And I mean, I'm just thinking out loud, but why not use machine learning directly on the original system? You think it's more challenging, or maybe Poincare maps?
Well, on the contrary, I think it might be more challenging on Poincare maps. But the thing is, Poincare maps are one of the most widely used tools to analyze dynamical systems. So it's something that's actually quite easy to get from a dynamical system. And when you look at when you think about it, and when you look at it, it's a very visual representation of what a dynamical system is. And machine learning techniques are known to work very well, you know, with visual representations, finding visual patterns. So I don't know, instinctively, it seems like something that matches really well, right? Yeah. So that's really where the idea originates from. And then, of course, when you think about it, Poincare maps are, in terms of mission design to liberation point orbits, one of the most important tools of low energy trajectory design, for instance. So the application also comes immediately when you think about it. So I think there's just too many coincidences there for something not to work out.
Right. Yeah. And is there some AI technique you're thinking about specifically for this work, or?
As of right now, it's still a bit too early, right? So we need to first, conduct a more thorough literature study than what we have already done, because I think you mentioned it before in the previous question, but machine learning techniques have been applied to chaotic systems in general already, and we have read about it. So we need to investigate exactly to which extent these things have already been applied. And together with the intern that's going to come work with us next month, we will a bit more refine which techniques we want to use. It's still a bit too early to be completely confident in what we're going to do.
So let's say if one is interested in this, I don't know, not me. When should they expect some results on this work?
Well, I think you can expect some published. I don't want to go too far, but some visible results maybe by June, something like this.
Great.
So stay tuned for this.
Great. Yeah, I will, and I hope someone else will. I mean, at least I will. It's really, I think there are promising ideas in the overlapping between dynamical systems and AI. And this one, yeah, the analogy with image recognition, I mean, face recognition and classification in images and the study of Poincare maps sounds compelling. So definitely.
Yeah, in the end, it's a very visual problem, right? So hopefully we can get some interesting results.
Yeah, yeah. And I read you used GPUs in your previous works.
Yes.
Have you applied this for parallelization related to AI, or was this something different? Because I was wondering, do you think GPUs are relevant in space in general, or should only people working in AI look for this kind of hardware?
So two good questions. So I'm going to tackle them differently. Let's start with, let's say, the use of GPU in my past research. That was actually a research conducted during my master thesis, so quite some time ago. I don't want to count the years because I don't want to sound too old. But basically, the idea was that we wanted to study asteroid aggregation. So the idea that some asteroids are made from an aggregation of smaller fragments. These type of asteroids are called rubble piles and are now believed to be a significant part of the asteroid systems. So the idea was to understand how these asteroids are formed and from which type of fragments they are formed, and to understand the inner structure of the asteroids. So we had two challenges. The first is that when you're talking about aggregation of asteroids, especially big asteroids, you're talking about lots of fragments. We're talking tens of thousands, hundreds of thousands of potential fragments. That's the first challenge. The second challenge is that the fragments were in our case complexly shaped, which at the time was the most innovative part of the research, right? Because usually people work with spherical fragments or cubes or simply shaped fragments. But in our case, they could be anything pretty much, polyhedrons. So when you think about it, you have two problems. One is that the contexts dynamics are going to be extremely complex due to the form of the different fragments. And the first problem is due to the sheer number of fragments and the mass distribution of the fragments themselves, the gravitational interactions are also going to be extremely complex to compute. So if you try to do this with a CPU, even with a proper parallelization, which already in itself can be a challenge, that wasn't a solution. You would get computation times that were the order of magnitude was several years. So definitely not something you want to do. So we had to find a way to first simplify the computation of gravitational interactions. And secondly, to compute it from a practical point of view, have something that you can obtain in a reasonable amount of time, right? So the first thing that we did was how can you actually simplify the computation of the gravitational interactions? And we did this using a Barnes-Hut algorithm, which is an algorithm that was used most in fundamental physics. It's a tree code algorithm. So the idea is to cluster together particles according to the range at which they are located and their mass and some decision considerations. And in order to reduce by several orders of magnitude the complexity of the computation of the gravitational interactions between the fragments, because in the end it's an n-body problem, right? So we implemented this on one side and tried to run it on a CPU, and again it didn't work, right? Because we simply didn't have access to enough cores for it to be efficient. But when you think about it, this kind of the algorithm was actually very suited to a GPU implementation and had been implemented a few years prior successfully on an NVIDIA GPU. So the idea that we had is can we just try to implement it on a GPU? And since we have access to much more computational cores, maybe this time things would work better. And luckily the answer was yes, things worked a lot better. And we moved from several months of computation time, several years of computation time in some cases, to about an hour in worst cases. So that was pretty impressive. Yeah.
Wow. Okay.
That was my first contact with GPUs. Right. But of course, that was a very specific case for which GPUs were extremely well suited, right? Where the operations that each core had to undergo were actually quite simple in some. They were quite simple algebraic operations. And we wanted a massively parallel system. which is what in the end a GPU is made for. And CPUs were just simply not, they did not allow us to have the same kind of distribution that we would have had with a GPU. Thus, we overcame this difficulty with the GPU. But now we come to your second question as to if GPUs are useful as a researcher, let's say in space and or only for AI. I think I already answered part of the question with the application that I mentioned. The answer is it depends. It depends. In the end, it's just, GPUs are just tools like CPUs are, and I mean, it depends on what you want to do. You have a nail, you have two kind of hammers, and you can probably, you know, put down the nail with both hammers, but one of them is going to be best suited than the other. So it depends on the application. For AI techniques and learning, obviously, when you want these such massively parallel applications with, again, simple complexity itself in the operations, what you want is a GPU most of the times. And this is what we do in our team. We train our algorithms on GPUs. But then when you have more complex operations involved, typically for mission design purposes, for example, and trajectory design, then CPUs are required. So the answer is it depends, but we use both. And for my work, at least as of now, I use both.
Right. Even now you're using both. Yes,
even now we're using both. Yeah. Right. Like I said, when we train our models, we try to do it as much as possible on GPUs. When we have these big data sets that we need to use for the training, we just use the GPUs, and we have access to servers for CPUs and for GPUs at ESA, so it makes things easier.
Right. And let's say the power of CPUs resides in their. I mean, a single core in a CPU is much stronger than a core in a GPU.
Yeah, I mean the frequency is obviously much higher. Yes. Okay. So that
so
already gives you an
idea. The single operation is complex enough, GPU loses. I mean, it's less competitive.
Yes, I would say. I mean, this is from my point of view, right? I'm not a computer scientist. So, but probably listening to this, there's going to be a computer scientist that's going to be screaming at what I'm saying. I apologize. That's my point of view of things, limited point of view. But yes, that's how I understand things at least. But then, of course, it's also, I mean, you have to think from the implementation point of view also. Because maybe when I said it before, it seemed easy to port the implementation of the Barnstead algorithm to a GPU. But even considering that an architecture for the implementation was already available in the published paper, it took a very long time to do it, just because, you know, the programming language in itself, it's its own beast. The logic behind it is completely different as you would do on a CPU. So it comes with its own challenges. It requires its proper parallelization. It cannot be as simple as you would do it on a CPU most of the time, right? It's not straightforward, is what I mean. What you want to do in a GPU is as much as possible limit data transfers between the different cores of the GPU, which is something that you can do more freely on a CPU, right? So you have to change the way you see things and the logic of things.
And so in this project, you worked both in a high-level coding language for the implementation, and then something in between to pass information to the GPU, or was this everything inside?
Yes, yeah, basically the core code was written in C++, and then the implementation itself, I mean, there was some code written in CUDA-C, which is the CUDA language that was required for the NVIDIA GPUs, but basically written as C language. And this was wrapped up nicely and then called from the C++ core code. Yeah.
Interesting. All right. So to wrap things together, let's say, also putting together nicely the way in which you talked about Poincare maps. You're focusing, as you said, on rendezvous. And my question is, how can convexification methods work in chaotic dynamical systems? And what's the relation between convexification and the typical linearization that you get when you do relative motion equations? Is there a relation?
Okay. So, like I said, I worked a lot on rendezvous and docking in two-body dynamics. That was the focus of my PhD. But by rendezvous, what I meant and what the community means in general is something quite general. In rendezvous, you have different phases, what we call the far rendezvous phase, and the close rendezvous phase. Most of the time, people divide it into these two different phases. Far rendezvous is what astrodynamicists call trajectory design. It's classic trajectory design, right? So within this context, I was interested in low energy transfers, in more, let's say, classic kind of impulsive transfers, low thrust transfers. I investigated all these things. And then for the close rendezvous part, which is the last few kilometers before docking with the target, this is where convexification techniques really shined, right? I know some other researchers applied convexification techniques to the three-body problem itself for trajectory design. If I remember correctly, the team from Politecnico di Milano, I think Francesco Toputo's team, works on this kind of applications. But I focus really more on the guidance and control part for the close rendezvous and for proximity operations themselves. And this is where I applied convexification techniques. That said, well, I'm still going to answer your question. So the relationship with the linearized dynamics is, well, the type of linearized dynamics you're used to when you work in the three-body problem are typically dynamics linearized about libration points, classically, because this is where you can find some approximations for the orbits that then you can exploit into full dynamics using shooting methods, etc., to build your own orbits, your halo orbits, whatever. But this doesn't work for near rectilinear halo orbits, which were the focus of my study. I was focusing on rendezvous on near rectilinear halo orbits, which are supposed to be the orbits hosting the future space station, the Gateway, to serve as an outpost for solar system exploration. So these orbits have halo orbit in their name, so they are halo orbits, but they are a different kind of halo orbit. They are at the edge of the halo orbit family, quite close to the moon, with a very low periloon passage and a quite far away apoloon passage. And when you look at them in the synodic frame, they have this very rectilinear shape, always facing the Earth, which gives it their name. And these orbits are interesting to put a space station there because they're extremely stable, which is quite different from the rest of the halo orbit family. That's the first distinction. And the second distinction is that these orbits are far away from libration points. So linearizing with respect to a libration point is not going to give you accurate enough results, at least in terms of guidance and control, and especially for a rendezvous when you want to have at the end of the rendezvous precision in the order of magnitude of centimeters, tens of centimeters. So that's not going to help you. And on the other side also, if you want to exploit, for example, say low energy transfers to near rectilinear halo orbits, they theoretically have unstable and stable invariant manifolds, but that are not exploitable at all for trajectory design purposes, just because these orbits are so stable that it doesn't make it's just not worth it. All that to say that we had to find other linearized models to work with. Hopefully you can linearize your system not around libration points, but around the position of the target spacecraft instead, and use this linearized three-body model within the context then of guidance and control. And then you apply convexification techniques. The big advantage when you do this is that you skip one step that is traditionally done in convexification techniques, which is moving from nonlinear dynamics to linear dynamics, because you've already done it. You've already linearized with respect to the position of the target. And you don't need to update this in your successive convexification algorithm. So basically, you have a constant way of linearizing your system that's done once and never done again later on. And this is going to actually speed up by a significant amount your implementation, your guidance implementation. So it does have a link.
And you say this because in standard convexification, you have to have a linearized surrogate model of the dynamics, which is changing in time as you evolve.
Well, the idea is to convert in convexification, move from your classic, traditional, often nonlinear optimal control problem to an NLP problem, right? So the way to do this traditionally is you start by linearizing the dynamics and discretizing the dynamics afterwards. So by linearizing your system, and since in the three-body problem your system is autonomous, you get rid of the time dependencies, so you don't care about the discretization, and you already linearize the system. So you basically skip two steps immediately, which is something that you cannot do for other applications. I'm thinking of, for example, landing. I'm thinking of maybe rendezvous in more complex dynamics. But in our case, we were able to skip this this part pretty fast. And this is actually very, very important because part of the accuracy of the method also comes from how you linearize your system and how you discretize your system afterwards. But we got rid of the discretization, at least for the dynamics. For the rest, we had to do it. But for the dynamics, we got rid of the discretization. So we didn't introduce any kind of inaccuracies because of it. Then the question was, how accurate were the linearized models? And luckily, the answer was when you start guiding from 100 kilometers from the target, you can use these relative models with very little loss in accuracy. So everything's fine.
Maybe you can say a bit more about the use of AI for convexification specifically. I didn't ask you which kind of AI algorithm techniques, ideas you're leveraging for this.
Again, there are two ways to see this. The one way is you have a hybrid architecture where you give more authority either to AI on one side, and then you can use the kind of AI techniques that you can see right now applied to trajectory design, these kind of things, or you give more authority to convexification techniques depending on the scenario, depending on the kind of type of accuracy that you want to reach, depending on a lot of things. That's one first venue, but that's, if I may say, maybe the boring way of seeing things. It might work, but it's a boring way. But then if you look more at synergies and how you can basically make convexification better with AI, one maybe simple application that I can see is how can AI be applied to approximate the constraints of your problem and convexify the constraints themselves and update the constraints within the guidance process, right? One very big challenge, because in the end, convexification is just about taking a very complex problem that you don't want to solve because it's too complicated and the algorithms have no guarantees of converging. Even if the problem itself doesn't seem complicated, maybe just the formulation is complicated. Taking something complex and turning it into something that is also very complex, but that you can solve very easily and very reliably, a convex optimization problem with convex constraints, etc. So you move from something that you don't know how to solve efficiently to something you know 100% you know how to solve efficiently. But the challenge is not transforming this into this. The challenge is making sure that when you solve the simplified convex optimization problem, or rather, when you solve successively, if you use successive convexification, the different sets of convex optimization problems, that you're still solving your initial problem, because it's very easy to forget your initial goal and to be very happy because you're able to solve something, but at the end, when you try to forward propagate your control profile, you find out that you don't end up where you should end up because you didn't respect the proximity of the two problems. So the challenge is to convert one problem into another one without losing the information in the dynamics and in the constraints. So that's where I think AI can shine, because this conversion is very problem dependent. Of course, there are some standardizations. It's quite standard how, for example, you can convert line of sight constraints. It's quite standard how you do the linearization and the discretizations to convexify your dynamics. I don't like saying convexifying the dynamics, but let's say it. It's standard, but it can be very problem dependent, and every time requires a lot of work. So the idea would be to alleviate this and to make it just more streamlined by the use of AI. And another thing that I would like to investigate is basically these techniques when then you solve the convex optimization problem. You're basically using trust region techniques, which rely on how close you are between two iterations of your algorithm to the solution that you use to linearize your system, right? Basically, the idea behind successive convexification is that you compute one solution and you use this solution to relinearize your system around this solution and iteratively find better solutions. But the question is, okay, if I look for solutions too far away from the solution around which I'm linearizing, then I'm going to be out of bounds. I'm going to be too far away from my linearization domain, and I'm going to have very bad accuracy with respect to the real problem. But if you don't move far away enough, then, well, you're going to stick to your solution and you're not going to be able to find the real solution to your problem, right? So the idea is, how can you adjust this trust region around which you're searching for solutions? And this can be, again, very tricky. Of course, there are some techniques to do it pretty much reliably, but the answer is it's problem dependent most of the time. So again, there is where I think AI can shine and can give us more insight into how the inner workings of these kind of things.
Right. And going back to the practical implications of this, is it again the two-body problem, and so the lunar gateway, or which
No,
kind
I
of,
think it's more general. In this case, it's more general because the objective is to find basically some design methodologies that are applicable to a wide range of applications in the space domain and guidance and control in general. So the idea, of course, rendezvous and docking is something I'm quite familiar with. That's where I'm going maybe to start applying it, but also for other problems, landing, for instance, debris capture.
Right.
We have all kinds of ideas, but applications are, I mean, we meant to design something that is going to be general enough to be applied in within the domain in different applications.
Great. Yeah, really nice. From the outside, it seems like in the Advanced Composite team, you're having a lot of fun.
It is a very fun team. Yeah, I have amazing colleagues, and we're having lots of fun with our research. So yeah. One of my interests actually in talking with you.
So I came to you actually about this position on Poincare maps, and I think your team is not sponsored enough for students that are looking for internships and opportunities like this. And so yeah, I would like to give my 2 cents to, I don't know, potential people joining this amazing not only team but also way of working, because you have so much freedom, it seems, that you're not constrained to one mission, as you said. It's not like you need to think top down, but you can just grassroots and
yeah, it's a privilege. It's a privilege. I feel like a very privileged person to be able to work in this environment because I mean it's a dream for a researcher, right? To be able to work on whatever you want to work, provided again it's interesting and new. But yeah, that's why you go to the advanced concept team. So yeah, I mean, if people want to join us, of course, I encourage them to join us and try their chance. We have calls for internships every year. Calls for new research fellows and young graduate trainees also every year. So yeah, hopefully some people that will see this will be encouraged to join us.
Yeah. Okay. Great. It was great talking to you. Thank you very much for your time.
Thank you for your time. It was great.